We want to look at another horizontal motion problem, but this time we're gonna make it a little bit trickier. And it's not the horizontal motion that's the issue, it's the force of tension. So we can have a case where the force of tension is not quite in the x direction, not quite in the y direction, it's kind of in between, but the object still travels horizontally. That's going to make things a little bit more complicated. And you'll see that here with this flying pig. So this flying pig is traveling in a circle. It's horizontal circular motion. But if we look at the free body diagram on this thing, we know that the tension is going to be along the string acting away from the pig. So that's going to be our force of tension. The pig itself is also going to have a force of gravity. And that's it. Those are the only two forces acting on it. Here's the problem that we have though. We need the force of tension that is in the plane of the circle. What we actually need is we need this component of the force of tension. So this force of tension can be broken up into two parts. There's this I'll call this Ftx, and we'll have this Fty. What we need here is we need that component of the tension in the x direction that's in the plane of the circle. So we need to find Ftx because it's in the same plane as the circle. This is where our efforts are going to get a little bit complicated. Now, the other thing is we're told that the angle between the string and the vertical is 30 degrees. What that means is if I look at this is my vertical here, what we're told is that this angle is 30 degrees. Well, this tension component for y is in the vertical direction, so I could also say that this angle here is 30 degrees. So if I blow up my tension for a second, if I kind of redraw my force of tension, so we have that Ft, and then we have our two components. We have this x component, which is what I really care about. And then we also have this y component. So what we know based on the question is we know that this angle in here, that is 30 degrees. So what we want to do is we want to see if there is a way to calculate this. Now we're going to have to kind of go back and forth between the two directions a little bit. So this is a little bit more of a complicated problem. But as always, let's start in the x direction. And I guess I should call towards the center of my circle positive, and we'll call up positive as well. So in the x direction, since I'm dealing with circular motion in this plane, I'm going to just say the centripetal force instead of the net force. And all it's going to be is this x component of the tension. That's great. Now, I need to find a way to get that component. Let's see what we can do. Well, if I look at my diagram here, I know that the tension in the x direction, it's going to be opposite to that 30-degree angle. What that's telling me from my diagram here is that the x component of tension is going to be this Ft times sine of 30. And then conversely, the tension in my y direction, that is going to be Ft times cos of 30. And keep in mind, some of you might be like, well, I thought x was cosine and y was sine. That's when the angle is defined from the horizontal. So make sure you draw your triangles. So opposite to this angle is my Ftx, so that's going to be my sine. And then adjacent to that 30 degrees, that's going to be my y direction, and that's where we're going to use cosine. So what I could say is that mv squared over r, this is equal to, well, Ftx, I could say that this is Ft times sine of 30 degrees. Now, in the question, we're told it's a horizontal circle. It's got a radius of 1.15 meters and it's 30 degrees, and we want to find that speed. Okay, I'm in a little bit of a bind. I don't know the mass, so that's a problem. I'm trying to find the speed, that's the objective. I know the radius. Well, I certainly know the angle here. I don't know the force of tension. I'm at a bit of a drawback right now. I don't know mass and I don't know the force of tension. This is a little bit of a problem. We're at a dead end in the y direction. let's see if we can use we're at a dead end in the x direction, so we want to use the y direction. So we're going to look at the y direction, see if that helps us out a little bit. So in the y direction, the net force in the y direction, and I'm going to use net force because in the y direction we don't have circular motion, like this thing is staying perfectly still. We're going to have that component of the tension, we're going to have that Fty plus this force due to gravity. Now the pig is moving in a circle, but the pig in the y direction is staying still. Like it's staying perfectly still in the y direction. Like the pig is not moving up and down. So we can say that the net force in y is 0. The reason for that is the pig is not moving up and down. So we know that the net force in the y direction is 0. Now the force of tension in the y direction, well, we could just say that that's Ft cos 30 based on what I have here. And then my force of gravity, that's just going to be m times g. Okay, there's some ways to get around this. Let's see what we can do. Let's solve this whole mess for Ft. So I know Ft cosine of 30 degrees. I'm going to take that mg to the other side. This is equal to negative mg. Or I could say that Ft is equal to negative mg divided by cosine of 30 degrees. So we're using the fact that the net force in the y direction is 0, so we have our tension component in y plus the force of gravity. So rearranging, what this is saying is that the magnitude of our force of tension, it's the negative of mass times g divided by cos of 30 degrees. We don't know the mass, we know g in cos 30 degrees, but what if I take this definition of the force of tension and put it in here? Maybe something magical is going to happen. So we're going to sub in Ft obtained from the y direction. This may help us out. We'll see. So I still have mv squared over r, and then I'm going to plug in that value for Ft, which we said was this negative mg divided by cosine of 30. Well, hang on a second here. I have a mass term on the left side. I have a mass term on the right side. Mass is going to cancel out. This is good. We don't need the mass, and that's great because we're not actually given anything about the mass, and that's a key thing to remember in some of these problems. If you're not given the mass and you think you need it, you will not need it. It's going to cancel out somewhere. So on the left side, all I'm left with is v squared over r, and on the right side I have this negative g times sine of 30 degrees divided by cosine of 30 degrees. So to solve for v, we're going to multiply both sides by r, and then we're going to square root. So v is going to be negative g times r sine of 30 degrees divided by cos of 30 degrees. If you want to simplify sine over cosine to tangent, go nuts. Again, we may see that that negative there is going to cause some issues, but again, g is the vector. We called up positive in our conventions. That means g has to be negative 9.81. So that's going to take care of that negative for us. We're told the radius is 1.15 meters. We have that sine of 30 degrees, and we're going to divide that by cos of 30 degrees. So we're going to square root all of that. It's a big, big mess here. A lot going on. But we can handle it. So we got 9.81 times 1.15 times sine 30 over cos 30, or just times tangent of 30. So we do that, we are going to get about 2.55 meters per second. So we could say that the speed of this pig going in a circle is about 2.55 meters per second. This is probably the hardest type of circular motion question you'll get. Even though we're only traveling in that horizontal plane, we still have to make use of trig a little bit. So as I mentioned, most of the trig's gone. this is the one type of problem where we'd bring trig back. It's definitely a little bit of a more challenging problem.